Okay, so this is part two of solutions in colloids. Here we're going to be talking about the specific colligative properties of solutions and relating this to what you're going to be doing in lab. Now, in terms of colligative properties, these are properties that depend only on how many particles are present and not what they are. Now, for us, we're going to specifically focus on vapor pressure. The more particles you have, the more your vapor pressure goes down. Oops, why is this going up? There we go. Move that down here. And that's because the more interactions you have between solute and solvent, the less likely it is that a solvent particle is going to fly off into space. Same thing can be said for elevating your boiling point. You have to put more energy in to cause those solvent particles to fly off into the air, so you end up having a higher boiling point that's necessary. Osmotic pressure is also affected, and you end up having a decreased freezing point because the more interactions you have, the more likely it is that those particles are going to continue to move and just not stall. And so that's kind of what we have here. So in terms of needing to know the quantity of solute that's present, we really need to talk about there we go, units of concentration. Now in 111 we focused on molarity. Molarity is really not a very good concentration value, so we're going to focus here on mole fraction and molality in parts per million as well. Now molarity is just mole of solute per liter solution. It's convenient because you measure out grams on the scale, you measure liters in your graduated cylinder, but really that's just lazy, because in actuality, if you think back to lab 2 for 111 when we're doing the density of that sucrose solution, density came from that table. Depending on the temperature of lab, you chose the density of your solution and you went with it. That means that this is temperature dependent. The volume changes with your temperature, and that's really not good. So while we use this on a regular basis, just keep in mind that it's not preferred. So thinking back to 111, how are we going to focus on molarity? Well, we could have something simple and straightforward like this, where we have 1.5 moles of sugar dissolved in 225 mils of solution. Calculate the concentration in terms of molarity. Please hit pause and actually try this, guys. Now, when we do this, we need to consider molarity is just moles of solute per liter of solution. And they actually do give us moles. So we need to actually go through and find the units of liters. Now, you're going to take that 225 and divide it by 1,000 milliliters in 1 liter, and you end up getting 0.225 liters. At this point, we have both the moles and the liters. We can go ahead and plug those values in. And so we can take 1.50 moles of sugar divided by the liters, and you get something like 6.67 molar. Now we could also kind of work in a different way and say you have a 5 molar solution. What volume do you need to have to get 1.5 moles? This is a little bit trickier. Here you want to consider we need to start with moles, and we're working towards liters. The only conversion we have here is molarity. This is moles per liter, so it's going to be our conversion factor. Now, in order to do that, we're going to take those moles. To cancel it, this needs to go on the bottom. So 1.5 moles divided by 5 moles in 1 liter It's going to give us 0.3 liters or 300 milliliters. There we go. Now, in terms of how complicated can this get, this is about the longest question I could give, and it would only be for one solution, not for two. Can you dissolve, you measure out grams in lab, you measure out 50 grams of NaOH and 50 grams of MgCl2, and you put it in 500 milliliters of solution. Calculate the concentration of each solution in terms of molarity. Well, we need to go from grams that you measure out to moles. We're going to do that using molar mass. From moles, we can get to molarity by just dividing by liters. So in order to find molarity, we needed to really have molar mass. So let's find our molar mass. For NaOH, we have 1 sodium, 1 oxygen, and 1 hydrogen atom. For magnesium, we have 1 magnesium and 2 chloride ions. Going to our periodic table, we know that sodium has a mass of 22.99. This is 16, and this is 1.01. Magnesium chloride, magnesium is 24.30, and this is 35.45. If you want to go further, you can, but I'm not going to. So plugging that in, we get the molar mass of sodium hydroxide as 40 grams per mole. Molar mass of magnesium chloride is 95.20 grams per mole. So now at this point, we have our grams, we have our molar mass. We can actually go to find our molarity. So for sodium hydroxide, we have 50 grams divided by the 40 grams in 1 mole, and then divided by the half of a liter. You get 2.5 molar NaOH. For magnesium chloride, 50 grams divided by the molar mass and divided by half a liter, 500 milliliters, you get 1.05 molar MgCl2. Hopefully that was a review from 111. I know I went kind of fast, but you should have seen it then, and it should be okay. Now, I just said that molarity is not very good. A better unit is molality, and that is because molality is not temperature dependent. It is all based on mass. So here this is the moles of solute dissolved in a kilogram of solvent, not solution, solvent. So for example, we could consider a solution of sulfuric acid where we took 12 grams of H2SO4 with a molar mass of 98.08 grams per mole. We dissolve that in 250 milliliters of water. What is the molality? Now, we're going to assume the density of water here is 1 gram per milliliter, although probably it's 0.995 or something. So, if we're looking for molality, molality is moles of solute per kilogram of solvent. So we need to consider that as we move forward. Now, the first thing we need to do is go ahead and find our moles. We've got grams, we need to find moles. We've got milliliters, we need to get kilograms of our water. So we can set it up, we can use our molar mass to go from 12 grams, divide by the 98.08 grams per mole, to get our moles of our solute. For water, you're going to take the milliliters of water, divide by the density, divide by 1,000 grams at a kilogram, and you get 0.25 kilograms. At that point, we can just take moles divided by kilograms to get 0.4894 molal. Okay? In addition here, guys, just keep in mind, do this stepwise. Make your plan the same way that we did in 111, and you should be okay. Due to technical difficulties, I don't have a pointer that seems to work. So we're going to, I can do a line, but it won't recognize curves. So with that, we're just going to type it out this way. Now for mole fraction. Mole fraction is the ratio of the solute's molar amount to the total moles of all components. This is just used as an X. It's an okay value, I guess. So let's go back to that same problem, and we're going to find the mole fraction of sulfuric acid. Now, we already know the moles of H2SO4. We need to find moles of water. So we're going to go from milliliters, use density to get to grams, and then use the density, the molar mass of water to get the moles of water. So setting that up, just like before, 12 grams of H2SO4 divided by 98 gives us 0.1223 moles of H2SO4. For water, molar mass of water is 18.02. It was given even though it's not typed up. Gives us 13.87 moles of water. So to find mole fraction is just the moles of solute per moles total. So you're going to take the moles of your solute and divide by the total moles, which is both solute plus solvent, to get your mole fraction of 0.00874. Now, those are really just the ways that we can talk about an amount of solute present. And so once you know how much is present, you can actually talk about how the colligative properties were influenced. And so if you consider something like vapor pressure, in general, vapor pressure is just the pressure exerted by the solvent's gas phase above the liquid level. Now, generally, you always have some particles leaving as gas, some particles coming back to the liquid phase. It's just, I mean, if you leave a glass of water out, it evaporates over time. The same thing can happen here. So the more particles you have, the more interactions that are present, the less likely it is to go up to the gas phase. And so here you can see you have a lot of vapor phase present. Here you have less vapor phase present. And it just vapor pressure goes down as you increase your solute concentration. Now the way we do that is by Raoult's law. Guys, I'm not going to give you a math problem on this, I don't think. Maybe in your homework, but not exam. In general, the idea is that your vapor pressure goes down in a direct correlation to the mole fraction of pure solvent. So here you've got the vapor pressure by component A, mole fraction of A, and this is pure A. And so depending on how much you have, if it's 75%, 0.75 times this will give you the new vapor pressure. So the less you have, the more solute you have, the less your mole fraction of solvent, and that is going to greatly affect your vapor pressure. The less you have, the lower the vapor pressure. It's a direct correlation here. Perhaps more important for us is boiling point elevation. Now there's that old wives' tale that says if you add salt, water will boil faster. That's a total lie. What it is, you know, you sit and you wait for a pan of water to boil, and you get a little bubble and then another little bubble, and eventually it might start to boil. You know, watched pot doesn't boil. But if you add salt, you actually are increasing the solvent-solute interactions. You're going to raise the boiling point, and it takes longer for it to boil, but once it does, you don't see a little bubble and then a little bubble. It starts more of a rolling bubble right away. Okay? Now here, the way that we find, ouch, that hurt. That really hurt. The way we find this relationship is with this formula. The change in boiling point is equal to a constant times the molality of the solute species. Now, Guys, that means of all solute species. So is it all of the ions? You can't just say NaCl. You have to say one Na, one Cl means you have two solute. If you have something like glucose, that doesn't dissociate, so it's just one. So you can go from molality to the change in boiling point to find the new boiling point, or we could look at it this way. Here we've got a solution that was prepared by dissolving 25 grams of glucose in 200 grams of water. So we have grams of solute, grams of water. The molar mass of glucose is given. What is the boiling point for the resulting solution? Well, oh, and they also give us the Kb. So we go back, we have delta T equals K times M. Well, they give us the grams of solute. That means we can find moles of solute. Then they give us grams of water, which means we can find kilograms of water. So that gives us the molality right there. Oh, and they also give us the molar mass, so we don't even have to do that. So what we're going to do is, considering what they give us, we have the delta T equals K times M, and we have these information. Now we can go ahead and start plugging in to find this molality, okay? Now please hit pause and try to find molality on your own. To find moles, you're going to take the 25 grams, use the molar mass to find the 0.1388 moles of glucose. To do kilograms, you're going to take the grams of water, divide by 1,000 to get 0.2 kilograms of water. So the molality is the moles per kilogram, or 0.6938. Now, we can then go back and use the K and the molality to find that the difference in boiling point is 0.35. Anytime you have something in water, the boiling point is 100. And so the boiling point has to go up. It's going to be 100 plus that 0.35, or 100.35 degrees Celsius. Where did it go? Same thing would be for freezing point depression. Freezing point depression is usually applicable during the spring semester when we get snow in January and February. They take a rock salt or something that has a lot of particles. They salt the streets. In doing that, it allows for, as snow to fall, it dissolves some of that salt, and it lowers the freezing point. It allows the water that falls to turn to the liquid phase and stay there, and that means that the roads won't be as icy. They're just going to have cold water on them. You can also think about that in terms of solutions that might be sprayed for a plane. You want, before a plane goes in the air, the higher it goes up, the colder it is, so that they will de-ice planes during the winter as well, and it's just to make sure that as you go up to those colder temperatures, it doesn't freeze. Now, going back to this, this is more relevant to lab because it's going to be what you do in lab. Here what you do is you monitor the freezing point. Using your freezing point and your K, you get to the molality. Once you have molality, you can find the moles of your solute, and then using grams and moles you can find your molar mass. Biggest mistake is going from molality to moles. People forget to multiply by the kilograms of solvent. Please make sure you're multiplying by kilograms solvent. The moles that you're using in lab this week is very, very, very small. It's usually to the -3 exponent, I think. So let's look at a problem. So here we have benzene, and benzene is going to normally freeze at 5.5 degrees Celsius. has a Kf value of 5.12. We're going to find the molar mass of a non-volatile solute, just means it doesn't dissociate, so the I value is 1. If a solution of 3.75 grams of that solute is dissolved into 61 grams of benzene, a new freezing point is 2.82. Now if you look at the equation, delta T equals KFM, you can't have a negative molality. You can have 0, but you can't have negative, which means when we set up this delta T, we need to make sure that it comes out to be positive. So we're going to have 5.5 and 2.82. We're just going to set it up so it gives us a positive number. And we can also plug in the K value because it's given as 5.12. And so now we have this much information. We can quickly rearrange that to solve for the molality. And you should get 0.523, but that is molality. That means it's moles of solute per kilogram solvent. And so to change to moles solute, you need to multiply by kilograms of solvent, which would be the kilograms of benzene. Now, if you do that, you get 0.0319 mole solute, which is a little large, I think, for what you're going to see in lab, but I can't quite remember. It depends on which solute they use. So then you're going to take the grams of your solute divided by the moles of solute you calculated, and you get the molar mass. You guys are actually going to use molar mass to find out what solute was used in lab. It's kind of interesting. Right. Now, the big thing about colligative properties, guys, is that they really just increase the amount of time that a substance is in the liquid phase. It lowers freezing point depression, raises boiling point, and lowers vapor pressure. It really keeps it present as the liquid phase longest. Fourth colligative property is osmosis. Now this is just, I don't know why the symbol isn't showing up, but it is the flow of a solvent into a membrane to alleviate pressure. It's related to molarity and a gas law constant. For the most part, again, I'm not going to ask a mathematical question on this just because of relevance. But the idea is solvent is going to transfer to a area where it has a lower solvent concentration to increase the overall volume or the overall interactions there, which is why, you know, students always joke that they're going to sleep on their textbook so that overnight the information flows from the textbook to your brain. It flows from the area of high solvent concentration to low solvent concentration. And I am going to skip that. Now, reverse osmosis is when you have a pressure applied to really try and force your solvent particles back into a pure state. It kind of works for a while. The problem is after a certain period of time, the amount of pressure you have to add, the amount of electricity you have to add is just not really worth it. Now, where osmosis probably matters most is if you have to have an IV. You want to add an IV solution that has the same concentration of solute particles as what is present in your blood cells. So if you added a isotonic solution, iso, just like isotope, means same tonic, I'm not sure how you would pronounce just the ending part, means that you have the same amount of solute particles in your blood cells as what you're adding as an IV. And so the solution, the water, solvent, goes in and out of your blood cells, no problem. If you have a hypotonic solution, here you've got, basically consider adding just pure water. Well, that means the solute particles in blood cells are going to be too high of a concentration. Water from the IV is going to flow into the blood cell and basically explode it, which is bad. Same could be said for hypertonic. Here it's bad. You've got too much salt, so the liquid in your blood cells flows out to try and stabilize the concentration of solute molecules that are being added, and you end up getting shriveled blood cells. There's actually a term for this. I think it starts with a C, but I can't remember what it is right now. So guys, remember, colligative properties only have to do with the amount of solute that's there. So if we're talking about an electrolyte or an ionic compound, you need to factor in the number of solute particles that are there. And so you're going to add this Van 't Hoff factor. This just means the moles of particles per moles of solute. So is it NaCl? Is it K2O? Just factor in how many particles there are. So you've got these interactions happening, and that's great, but it comes down to how much impact do you have. If you add something like KCl, there's one potassium, one chloride. Here there's one potassium, one nitrate. So your Van 't Hoff factor is 2. But something like this, sodium phosphate, you have 3 sodiums and 1 phosphate, so you have an impact of 4. And so what we're going to do is we're just going to add this Van 't Hoff factor here to make sure you take into account the number of solute particles that are present. The last thing I need to say is about colloids. Colloids are a suspension of tiny particles that do not settle. It's really just an emulsion of 2 immiscible substances. They tend to be cloudy, so they scatter light. The best example is really milk. Now, a solution, you have very small particles. They do not scatter light. They tend to be clear, kind of like the nickel solution, the copper solution you guys had in lab 4. They're clear. You can't see the individual components. A suspension is something that you can mix it up, but it pretty quickly falls back out. So something like mud, you can mix that up, but if you watch, the dirt settles very, very quickly out of solution. A colloid has medium-sized particles and will stay mixed for a period of time. I can tell you on a regular basis, my children try to leave milk containers out, and it's almost like a game of time-lapsed Russian roulette. When did the milk settle and go bad? In fact, I found a cup a few minutes ago in the bunk bed. I don't know. I haven't seen that cup in weeks. It's going to be disgusting. But the idea is you have a colloid, it stays suspended until it starts to settle. And if you've ever seen milk spoil, it is a very clear separation that happens. So if you look at colloids, things like smoke or dust, you ever walked into a room and you can just like an old room, and you shake out a dusty blanket, that dust stays suspended for a while. Solid and liquid, something like starch and water, ink or paint. Paints are very much a colloid because they stay mixed for quite a while. Solid things like gems or alloys. A liquid could be dissolved in a gas, things like clouds, fogs, mist. Liquid, milk, mayonnaise, butter, those are all emulsions. Liquid into a solid, things like jellies or gels, even an opal. Gas in a liquid could be things like whipped cream or meringue. And then a gas could also be in a solid and have like a pumice type of situation. You could also have something like a soap or a detergent where you really take into account the interactions that are happening. You have the hydrophobic tail, the hydrophilic head, and they are going to try and associate like ends with like ends. And so if you had dirt, dirt would be carried away in the nonpolar center. This gets associated with water and gets washed away. So in general, a colloid is going to really only be separated or destroyed by heating or adding an electrolyte, or occasionally, like in the instance of milk, you can do it over a period of time, but it's a long time. You have to interfere with those suspensions in order to get that to happen. That is it for this unit. We will pick it up again in the next unit.